Hello and welcome. This is technically it's an AS video. It's actually AS for the maths. Obviously you're smart enough to be able to read. This is quite a short video. It's just understanding what complex numbers and imaginary numbers are. It's a short video, as I said, because I'm just in this video going to introduce the theory of it. I'm not actually going to go through so many questions because there's no real need to, as this topic is fairly self-explanatory. When you understand it, that's it. You understand it. There's only two things to this, really. It's not that difficult. So let's start with that first one, the imaginary numbers. Now in maths, if you got something like the square root of minus 16, that if you put that in your calculator or if you try to work that out, what you'd get is that's not equal to any real number. In other words, in maths you get a maths error because it's not equal to anything, because obviously 4 times minus 4, well, they're not the same number, but that give you minus 16. However, so we can't work it out that way in a calculator. Now most people will be lazy and I can't be bothered, it's not equal to anything, that's it, stuffed. But because we can relate this to something we actually do in C1, so it's that simple, even though it's further maths. What we do is we say, okay, well, say if this was, to put it in perspective, we use surds. We're using surds because that is in a surd format. I mean, it's a negative, granted, but it's still in a surd format. Now, what you would do in a surd format, say if this wasn't root 16, let's say if this was root 72, for example. So if this was root 72, what you'd do, so this is just to remind you what surds were. 72 is 8 times 9, so it'd be root 8 times root 9. So therefore, it'd be 3 times 2 root 2, which is obviously 6 root 2. Which is obviously, that's an obvious surd. But what we did is we denoted this into one square number and one that's not square number. So we're going to do a slightly similar thing. I mean, as I said, it's not specifically that similar, but anyway, basically, what we do, the idea of splitting it up into two surds, so splitting it up into two square roots is what we're going to apply to this. So you don't really need to have that other square number there, really, but you know, it'd be nice if you could. So what we're going to do is, okay, so we get this root 16, and we're going to split it up into two square numbers. So therefore, root 16 is equal to root 16 times root minus 1. Now, we can do root 16, so that is equal to 4 root minus 1. But we can't do anything with this root minus 1. So what we do is we call this an imaginary number, because we're imagining it, it's not real. So that's why when you see this is not equal to any real number, we can apply it to over here. So if we say we're going to let this number, letter, we could call it I. So let I equal root minus 1. And if we let I equals root minus 1, this is going to be, instead of 4 times root minus 1, it's going to be 4 times I, hence 4I. So this I basically is going to stay the same. We're going to always assume it's I to be root minus 1. In this case, so therefore anything that is root minus 1, we're going to say, oh well, that's I because that's imaginary, we can't do it. But what we do is we always take minus 1 out of this, we always turn it into a positive. So no matter what this is, that could be minus root 36, so let's do that. Say minus root 36. Now obviously, we take minus 1 out of this, so that's root 36 times root minus 1. Therefore, it's 6 root minus 1, and we said root minus 1 is I, so therefore it's 6I. And because that's not a real number, we call these imaginary numbers. So anything with an I in it is an imaginary number, because we're imagining it. It doesn't really happen, but mathematicians like to be awkward and say, okay, well this can't be done, but I'm going to make it be done. So anyway, that's what we mean by an imaginary number. It's just, basically in this case, it's just root minus 1. So, sorry about the colour, by the way, I should apologise if I had at the start, but I think it's just the camera's probably had enough. I don't blame it, to be honest. But anyway, so that's what an imaginary number is. Now the other half of this video, the eagle-eyed viewer would have spotted but you've not gone through complex numbers. So what is a complex number? Well, to kick off the bat, it's something in the form a plus bi. Now, we know I is an imaginary number. Bi, sorry, that's an imaginary number. However, the a is more simple than it would seem. This a is just anything, could be any number. So therefore, it's just something we call a real number. Now, a real number is anything, any number that you can think of. So that'd be 22.2, 77.8, 21.9, anything. It's not an integer, well it could be an integer, but it can be absolutely anything. Minus 7,655.00225597257996, that's a real number, because it's real. But anyway, the idea of this is to say a complex number is made up of an imaginary and a real number. This imaginary number, we said, that was root minus 1. But this imaginary could be anything. We call it I, just for short. So some people write J, but I like to be awkward and write I, because I. So, right, okay, so that's what a real and imaginary complex number. But when will we ever get this? Because when we get a root minus 16, we don't get it in this form, we just get 4i. So let's not give it a plus. And you can't go, oh, well, we want to shove a 0 in there, that's any number, isn't it? Surely then that's in the form of a complex number. Well, it's not. Partly because that's cheating. And mathematics don't like to cheat. Just like I don't cheat death. It cheats me. Anyway, so when will we get something like this? Well, if you think of this as, I don't know, let's say we'll call I root minus 1. So that's a plus b times root minus 1. Now, when would you ever get something like that in the form, in a formula? You kind of giving it away there. So when would you get a number plus another number times the square root of something? Well, generally you might see it like this. So you might see a plus b root, let's say that's minus 1, over c. Now obviously I'm trying to not give it away, because if I wrote it as it would, I'd give it away. So if you've not got what it is yet, we've got a plus b times b root minus 1 over a constant. A, b and c are constants, by the way. So that just means 3, 7, 8 or whatever, 3.1. So this is just numbers, real numbers. So what we get, what this is representative of, what I'm trying to highlight here, is this form. We get something in this form from using the quadratic formula. Okay, so therefore you only use the quadratic formula when, weirdly enough, you've got a quadratic. But you only use a quadratic formula to solve the quadratic, A, when you're lazy, or B, when it doesn't factorise. Now when I say it doesn't factorise, what I mean by that is not the fact that, well, yeah, it doesn't factorise. So, and let me think of something. So x squared plus 420x plus 2. That equal to 0. That does not factorise. It's a quadratic, but it doesn't factorise. So therefore, this minus 1, root minus 1, is actually saying that's the square root of b squared take 4ac. And 4ac must be bigger because we've got a minus under the square root. So therefore, we have an imaginary number. That's when we have we have to use this complex number thing. So if we were to draw that, now I don't know what that looks like, but where the intercepts are, but it's not going to go through the x-axis, and that is because this discriminant. Now we don't just teach you in maths things that aren't real, that don't exist. We teach you in maths because we're awkward, and it does exist because people have got up one day and thought we're going to make this awkward for people, so that people in the future like you are going to go, oh, maths, eh? So anyway, what I'm trying to state here is the discriminant is right. Yeah, we don't have any intercept because it's minus, but they're real intercepts. We have an imaginary intercept, but we don't show it because guess what? It's imaginary. So it's going to look something like this. I mean, something like that. As I said, I'm not 100% on that, but it's going to look something vaguely. Basically, it's not going to intersect the x-axis because, as we said, the discriminant is minus, so it's not going to have any solutions, but it's going to have an imaginary solution. So you could use this idea for a cubic, and obviously when you factorise a cubic, you could, take out x, minus 1 is a common factor, and then have a, so say for example if you've got x cubed plus 2x plus 3. Now this, as I said, would not factorise to this, but I'm just trying to show something. So this x cubed plus 2x squared plus 3x plus 7. Now this is not going to factorise this, but I'm just trying to explain what I said there. So you say you take out x, you say you were told x take 1 is a factor. So say if you were told, this is using the Factor Theorem. So if you don't know what the Factor Theorem is, do check out my video on that in C2. So the Factor Theorem states that when f of 1 is 0, then x take 1 must be a factor. Okay, so you could use the Factor Theorem to work that out, but then you take x take 1 out of this, so then you get something like, I don't know, x squared plus 2x plus 7. Now obviously that doesn't work because it's not factorised, but I'm just trying to show you. So if you've got a cubic, you could use the remainder theorem to take out a factor, and then you could use a quadratic formula to work out what the roots of that are. Now you would get a root of, say that didn't factorise, so this x squared plus 2x plus 7, that's, as we said, the discriminant of that would be negative, so it's not going to have any solutions for the quadratic, but we've still got a solution of x equals 1. So therefore, the cubic is going to look something like this. So where it's just going to have one intercept there, so it's only going to have one real root, but it's going to have an imaginary root, so you have to state that as well in further maths. So that's what complex numbers and imaginary numbers are. Imaginary numbers are numbers which we are root minus 1, or a negative root, and then this complex number is just basically a mix of a real number and an imaginary number, and we get this idea from the quadratic formula. So therefore, we get a complex number when you're using the quadratic formula. That's essentially what you do. Obviously, you could use a quadratic formula on a cubic, but you'd have to take out a factor to make it quadratic, which is what we just demonstrated there. But as I said, hopefully I've not scared you off too much in this video. I've just tried to be a bit exciting about this because, let's face it, this little topic here isn't that good. I mean, it's interesting, but it's just generally using C1 stuff. So it's a nice introduction to further maths. Because it's only AS, it's not going to be that challenging. Well, obviously further maths is, but what I'm trying to say is you're just going to be, as like this, you'll be using C1, C2 stuff at this stage anyway. So thanks for watching. We're going to see you in the next video. We're going to do a bit more on this idea of, well, we're not going to carry on as much with complex numbers because that's as far as complex numbers really gets. But yeah, just have a look at the next topic. We're just going to go on complex conjugates. I can't say it properly, but it's just another step forward in that idea of complex numbers. But that's what a complex number is. Thanks for watching, and we'll see you in the next video. Oh wait, sorry. Just before I go, unless if you've clicked off, then stop here. But if you haven't been watching this for a little bit longer, I will be doing. I haven't really gone through any questions as such. I've gone through a few examples of questions, but I've not gone any through exercises or whatever per se. That's because I don't currently, at the time recording this video, I don't currently have any classwork booklets with me because I'm the only person in the class. So therefore it'd be a bit pointless to have a classwork booklet. But I'm going to get some probably before, well, hopefully before I record the next video, because for that I'm going to go through some examples, some questions. So for those of you, I don't know who would have this booklet, but if you do, or I'll just be going through some extra questions, then some past paper questions, hopefully, on this topic in the next few videos. So thanks for watching, and I'll see you in the next video. I'm not going to come back on the screen, so see you later. Bye.